So right now, all of you are grabbing a notebook, piece of paper, pen, pencil, the one that's already next to you, because you know that you have got to be ready to take notes in chemistry class. And we're going to start from the very beginning. We're going to start from the basics. So what I have here is scientific notation, and I've got all the different pieces of the notation. So this is a way of writing very large or very small numbers. Just makes our life easier. Even if you don't believe me right now, trust me, it will make your life easier to use scientific notation. There's three pieces. There's our coefficient. So this here is my coefficient. There's a base. This is the base number. And then there's an exponent. And I'm just giving us arrows to make it really clear which part is which. Coefficient, base, exponent. Some of these terms we're familiar with. I'm very much hoping that you know what an exponent is, because if you don't, it'll just make my life more complicated. Base, it's just the base of the exponent. It's going to be easy for us. It will always be 10 for scientific notation, and I'll explain why in a second. And then the coefficient is a number. It often has a decimal point, but it only has one digit in front of the decimal point. Only one digit in front of decimal. Okay. I'll give you a second to write this down. Give me a second to open my Pomelo. Coefficient, base, exponent. The exponent here means exactly the same thing that an exponent means in any other context in math, right? And I'll show you an example of that. This is technically a math concept that we're applying to chemistry. Math and chemistry are intimately related. I'm really struggling to open this thing. I want my snack. Dunsy. Okay. Alrighty. I'm going to erase what I've got annotated, and then we are going to look ahead and just look at a couple more notes. So actually, let me rewrite that phrase I had, or the scientific notation I had in the previous page. 5.6 times 10 to the 6th power. This is exactly the example from the previous slide. But let's take a look at like all the different notes. I've already mentioned these, but I'll restate them because here I've got them written out. So my coefficient must be greater than or equal to 1 and less than 10. So another way of saying that is I can only have one digit in front of the decimal point, right? So if it's at least 1, it can't be smaller than 1. If it's smaller than 1, then I have a 0 in front of the decimal. No bueno. It has to be at least 1, and it has to be less than 10, because once it's 10, you have two numbers in front of the decimal, right? It can be 9.99999. That's less than 10. That's fine, but it can't be 10. So the coefficient can only have one number in front of the decimal. I'm updating attendance. The base is always 10. Base is always 10. And then my exponent, specifically in scientific notation, my exponent shows the number of times that my decimal point needs to be moved to write the number in standard notation. And right now that phrasing doesn't quite make sense. I'll show you an example of how to do that in a few minutes, and hopefully that phrasing will make sense. But we're going to be moving this decimal point around, and the number of times it's moved is directly connected to this exponent. And that's why I always have a base of 10. Because when you multiply something by 10, you move one decimal place, right? You make it one decimal place bigger, one decimal place bigger, et cetera, right? So there's a very direct correlation between this 10, this exponent, and me moving this decimal point around. I'll give you all a second to copy this down while I take a bite of my snack. The one problem with pomelos is that they have to be peeled. You can't eat the peel because it's really, really tough. So they're just a little messy. I should probably mute myself when I'm chewing, right? Common courtesy. Okay. So we've had a few minutes to write this down. Coefficient has to be more than 1, less than 10. Base is always 10 because we're moving decimal places around. And when I multiply or divide by 10, that's when you move a decimal position, right? And then the exponent is directly related to how many times that decimal point is moved. What I would like to do right now is just to go through two examples. I'm going to do 2 examples now and then 2 different examples in just a minute to show you how exactly we write out the scientific notation and how it's mathematically connected to the standard notation. So here's a very simple example. I have 1 times 10 to the 7th power. What I'm going to do is I'm going to expand on this definition of the exponent using the math skills that you and I both have to write this. Anytime I have a number to a power, right? 10 to the 7th power. Anytime I have an exponent, what this exponent means, the mathematical definition of this exponent means I'm taking this base and I'm multiplying it against itself this many times, right? So in this case here, if I have 10 to the 7th power, I'm taking the number 10 and I'm doing 10 times 10, 7 times. So 1, 2, 3, 4, 5, 6, 7. I'm multiplying 10 against itself 7 times. Pause. In the chat, can you just check in with me that yes, this makes sense? Yes, I know how to do that. I understand an exponent. Just check in. If you don't, please let me know because that tells me how much I need to go into detail. Quick check-in in the chat. Yes, I understand what an exponent is. Cool, 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 cool. Great, beautiful. I just want to double check, right? I was hoping that this makes sense to us, and it seems like it does because then I can move on. And I'm not going to spend too much time talking about how I expanded this. 10 to the 7th, 10 times 10, 7 times. Then I literally took a calculator and I did this math. 10 times 10 times 10, blah, 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 and I get the number 10 million. So this here is equivalent to 10 million, aka 10 to the 7th power is equivalent to 10 million. My first example is very simple. My coefficient is 1, right? Any number times 1 is that same number. So if I have 10 million times 1, it's just going to be 10 million. And this is my final standard notation expanded form. Right? I'm going to use this phrase, standard notation. It just means the full number. Right? And then scientific notation means these the part with the exponent and the base. Here, this first example is pretty simple because I've just got a 1. I've got it expanded. I'm showing you how these mathematically are related. Let's take a look at a slightly more complicated example. Let's look at 6.54 times 10 to the 7th. So now my coefficient is 6.54. Let me just do a quick double check. It's greater than or equal to 1. Yes. It's less than 10. Yes. So this is good. This is written correctly. Also, just double check. I only have one number in front of the decimal. Perfect. This is good. 10 to the 7th. So that's 10, 1, 3, 4, 5, 6, 7. 10 times 10, 7 times. 6.54. Let me multiply these against each other. So 6.54 times 10 million. So if I do that math, I'm going to get 65,400,000. So this number and this number are equivalent, right? They're the same exact number. Same exact number. I'm going to pause a second, just give you guys a chance to copy this down. Give me a chance to eat my snack. I'm going to mute myself so I can eat. So hopefully this so far is making sense. We're able to see that these two numbers are numerically equivalent. They mean exactly the same thing. But the whole reason we're doing scientific notation is to make our life easier. If I have to go through this process every time, that's not making my life easier. I want to show you this all the way worked out just to prove to you that this phrasing, this expression makes sense. But now what I'd like to do is to show you the cheat sheet way, but not the cheat sheet, the quick way. What's that word? Shortcut. That's the word I'm looking for. I want to show you the shortcut way to go from this expression to this number. I'm just going to erase these lines and give myself a little bit of space to draw. So there is a shortcut way to write out scientific notation. So here I have 65,400,000. At the end of this number is a period, right? At the end of every number is a period to say like, hey, number ended, decimal point, not period, decimal point. What I need is I need a coefficient that only has one integer in front of the decimal point. So let me go count how many spaces away that is. Okay? So that would be right here. I need my decimal point to end up right there, right after the 6. I didn't quite leave myself enough space, but I want it to be right there, right after the 6. So let me count how many spaces that is. So that would be 1, 2, 3, 4, 5, 6, 7 decimal spaces away, right? 7 decimal positions from here to here. So let me rewrite 6.54. 6.54. I'm writing on all my integers, 6.54. And I move my decimal point from the end to this position right here. So what I need to summarize here with my exponent is how many decimal positions was that movement? Well, it was 1, 2, 3, 4, 5, 6, 7 positions. So what I do is I take my whole big number. I look at how many spaces is my decimal point going to have to move to get to the right coefficient, and then I summarize that using this base exponent expression. Let me do this one as another example. Right, so I'm starting here. I want my decimal to be here so I can write out my coefficient. So that means it needs to be moved 1, 2, 3, 4, 5, 6, 7 positions. So if my decimal point is moved to that position, I'll have 1.0 as my coefficient. And then I'm going to say 10 to the 7th to summarize that it was moved 7 times. Some of you are looking at this and you're like, Ms. Shaw, I still would rather write out 10 million. It's still easier for me just to write out 10 million. And sure, I'm not going to argue with you. I am going to argue that you don't want to be writing out all these zeros. You really don't want to be writing out all those zeros. Okay? So just to remind you, this is a number for a mole. This is not going away anytime soon. This number is going to be around for a very long time. We're dealing with a number of particles. It's insane, insane numbers because those particles are so tiny, right? So it's, in the long run, it is helpful to put things into scientific notation because you just get such massive numbers that are impossible to deal with otherwise. So I just want to bring it back to reality of like why this is helpful to us. I want to pause and see if there's any questions. I want to see if anyone has any questions about how I went from this standard notation to the scientific notation. Would it be helpful to see another example? Cool. All right. People are saying yes. Let's just look at another example. Make sure we're doing it right. Yeah, happy to do that. We're ahead of schedule, so I'm more than happy. I'm going to just draw a line here because I was that kid in high school that I now as a teacher don't like, that would just draw lines to like separate things on my paper. Anyways. It took me until college to realize that paper is really cheap and I can just use paper. I don't have to fit everything into one sheet of paper. Okay, let me look at an example. Let's do 5, 9, 8, 2, 0, 0, 0. I'm literally pulling this out of my the recesses of my mind. I'm making this up as we go. So here is a giant number. This is a standard notation, and I want it to be in scientific notation. So what I'm going to do is just start by marking my decimal point because it's at the end of the number, right? And then I'm going to look for my digits at the beginning, my non-zero digits. So I have 5, 9, 8, 2. At the end, this part here is going to be my coefficient. These non-zero numbers are the coefficient. And the decimal point is going to have to be right after the first digit, the first number. So my decimal point is going to end up here in my coefficient. Now let me count how many spaces I need to move my decimal to get it from the end to there. Okay. So I know that my coefficient at the end is going to be 5.982. And now I need to count how many spaces do I need to move this decimal to get from the end to the front. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I had to move this decimal point 10 spaces. So I'm going to summarize that with my exponent to say that, yep, correct, Jessica. This number had to be moved, or the decimal point had to be moved 10 spaces. So I get this coefficient times 10 to the 10th. If I want to undo this number and write out the standard notation, what I would do is start with a coefficient, and I would go the other way, right? So here I move my decimal point from the end to the coefficient, summarize how many times it was moved. Now let me undo the scientific notation and write it in standard notation. So here's my decimal point that I'm starting with. I need to move it 10 spaces. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I've got all these empty spaces that are going to be filled up with zeros. So all these empty spaces end up being zeros. So what I did here was I took my coefficient and then I moved my decimal point to undo the scientific notation and write it in standard notation. Pause. Questions? Pause. I want to see if there's any questions. In hindsight, it's probably better. I shouldn't be recording while I'm eating a snack, but it's okay. Now everyone else has to see what you guys have to deal with because third period Miss Shaw is always eating. Okay. These are examples of scientific notation, expanding it to the standard notation and then reducing it back to scientific notation. I want to point out that my exponents here are all positive numbers. it is possible to have scientific notation with negative numbers in your exponents. And that's my next example that I'm going to show you. I would like to erase all my annotations and show you negative exponents. Positive exponents are one thing, negative exponents are something else, and you're expected to know both. So I'm going to erase here. Again, I'm recording this, so you'll have access to all these notes later. Let's take a look at negative exponents and see how they're different. First, I want to do a check-in in the chat. How many of you have dealt with negative exponents before in math? How many of you have seen this and know what it means? It's okay if you haven't. This is me just getting a poll, so I know how much to explain. How many of you have seen negative exponents before? Yeah, it depends, I think, if you're in IM 1, 2, or 3. Okay. I'm seeing some yeses, some maybes, some nos. Okay, so there's a blend. I'm going to give you a little bit of the math background of negative exponents, and then show you how to do the scientific notation, because you don't actually really have to understand it to be able to do the scientific notation. You just have to remember which direction to go. So a negative exponent, 10 to the minus 7th, is the same thing as saying 1 over 10 to the 7th, right? So whereas when I have 10 to the 7th, this is a giant number that's getting bigger and bigger and bigger. Here, I'm getting smaller and smaller and smaller, right? Because 1 over a giant ass number is a small number. I should watch my language. So in this case here, negative exponent means that my number gets smaller and smaller and smaller. So the way that I've written that out, I'm going to erase my work. The way that I've written that out is that instead of multiplying by 10, you're dividing by 10. So I'm multiplying by 1/10 each time, right? So 1, let me write it out this way. 10 to the minus 7th is equal to 1 over 10 to the 7th, which is the same thing as saying 1 over 10 times 1 over 10 times 1 over 10, 7 times. I'm running out of space, so I'm not completing it. But these are equivalent expressions. 10 to the minus 7th is the same thing as 1 over 10 to the 7th. So it's 1 over 10th times 1 over 10 times 1 over 10, 7 times. 1, 2, 3, 4, 5, 6, 7. After I multiply these, this is the number I'm left with. So this is 1 millionth, right? Tens, hundreds, thousands, 10,000, 1 10 millionth? I don't know. 1 very small-th number, right? You can see that it's all behind the decimal point, so this is a very, very small number. My coefficient in this first case is 1, so 1 times anything is that same number. Let's look at a slightly more complex example where I've got a coefficient that isn't 1. Here I have 6.54 as my coefficient. I also have 10 to the minus 7th. I did that on purpose just to not make it too complicated all at once. So I'm doing 1/10, 10 times, 7 times. 1, 2, 3, 4, 5, 6, 7. I get 1 millionth or 1 10 millionth or whatever. And then now I need to multiply it by 6.54. Feel free to do this in a calculator if it makes you feel better. But in the end, 6.54 is going to go here where the 1 is. So I have 1, 2, 3, 4, 5, 6 zeros, 1, 2, 3, 4, 5, 6 zeros, and then my coefficient. I acknowledge that negative coefficients are a little bit more uncomfortable. Sorry, not negative coefficients, negative exponents. Negative exponents are a little bit more uncomfortable. Let me change colors. That just makes me feel better to have multiple colors. I want to show you how to go backwards, how to take this standard notation and to put it into scientific notation when I've got these itsy bitsy numbers. So honestly, this is how I do it. I look at my number and I'm like, oh, check this out. It's a teeny tiny number. It's an itsy bitsy number. Already, automatically, in my head, warning bells are going off that I'm going to have a negative exponent because this number is smaller than 1. Okay? It's less than 1, so I know I have to have negative exponents in my scientific notation. So my decimal point right now is here. I want it to be behind the first integer, the first non-zero digit. So 0, 0, 0, 0, 0. Okay, here's my first number that isn't 0. I want the decimal to be right behind that number. So let's see how many spaces I had to move it. To move it 1, 2, 3, 4, 5, 6, 7 spaces. So I'm going to rewrite this coefficient with that decimal in the new position. And then I'm going to summarize times 10. That's all the same. I have to move this 7 spaces, but I started with a number that was smaller than 1. So I'm moving it negative 7 spaces. Let me do this one here as an example as well. So right now I'm starting with this decimal point in the beginning there. I want my decimal, for scientific notation, I want this decimal point to be behind the first integer, after the first non-zero number. So 0, 0, 0, 0, 0, 0. And then I see 6, 5, 4. The decimal is only after the very first number, after the 6. Let me count how many spaces my decimal point needs to move to get to that position. So it needs to move 1, 2, 3, 4, 5, 6, 7 spaces. So if I rewrite this, my coefficient is 6.54. And I have to move my decimal point 7 spaces, but this number is smaller than 0. Sorry, smaller than 1. Smaller than 1. It means that I'm moving negative 7 spaces. Pause. Questions. I want to see what questions are coming up for people. And I can show you how to go the other way as well. You guys want another example? Not getting any responses. I'm going to show you another example whether you like it or not. And I'm going to go both ways with this example. And then I'm going to stop and give you some time to practice. Because honestly, this is one of those things, like it's important to get an explanation and to know how it works. But really the learning happens when you practice it and you like figure out the patterns on your own. I'm going to clear these drawings. And then I'm going to do this. I'm going to do this. And then I'm going to give you another example. Let's do green. Just like changing colors. Let's see. My number is going to be 0.00251. Okay. Leaning a little bit, and that's okay. This is my number. I need to take this number and write it into scientific notation. Let me do another color crazy here. Okay, so let me check this out. Here is where my decimal point is starting, right here. And I want my decimal point to end up behind the first integer. So these are all zeros. 0, 0, 0, 0, 0. stop at the first, here we go, 2. I'm going to put my decimal point right after the 2. That's where I want it to end up. Now what I need to do is count how many spaces, how many decimal spaces does it have to move from the start to this new position in the coefficient. So it has to move 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 spots. So my number is going to be 2.501. Even though there's a 0 here, because there's a 1 there, I write all those numbers in my coefficient times 10. I had to move this 12 times, right? But I started out with this number smaller than 1, so I know that this movement is negative. So negative 12 spaces. Now let me show you how you could undo this to write out the standard notation. Okay? Now let's say, hey, you're given this number and you want to write it in the standard notation. You want to write it out. Okay? Let's do a little bit of analysis first. So I got 2.501, that's my number, that's my coefficient. My exponent is negative. Okay, so because my exponent is negative, I know that I'm going to be moving my decimal point that way to make my number smaller and smaller and smaller, right? And I know that because of this negative sign here. So let me start by writing down my coefficient, 2.501. And then I'm going to move this decimal point 12 spaces to the left so that this number gets smaller and smaller. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Boom, right there. Every single empty space, every single empty decimal space that I moved, my decimal point is going to be occupied by a 0. Boom, 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 boom. And I like to put a 0 in front. Okay. So this is the standard notation written out, and I figured this out using the scientific notation. Here's the scientific notation. I can figure this out using the standard notation. Go back and forth between these. So if I have one, I can figure out the other. Questions?